Snap, crackle, pop. Wonder what they have in common besides the cereal.
Well, they're all sounds, and today to help explain more about the speed of sound and the way sound works is our wise guy, Matt Sellen. Matt, thanks for coming in today. Getting musical with the guitar and some other stuff.
Well, I just had an excuse to bring it. I really like my guitar.
You do look
We
cool
do
when
too.
you're carrying one around, you know?
So we're all gearing up for next week, because next week Dr. Z and I are going to talk about ultrasound.
Oh.
Which is, you know, what they do. It's a machine that they use in hospitals to probe into your body without cutting into you. And to do that, you have to understand that sound can propagate through things other than air, like it can propagate through your body through water, which is mostly what your body is. So we'd like to measure the speed of sound in water, and we'll get to that next week. So today we're going to just measure the plain old speed of sound in air and in aluminum.
Okay.
And this is the most annoying demo ever. You're going to love this one.
I think we've had the singing rod.
I think
here
you've had it before, but this one's even more annoying. It's louder than the last one we had.
Looking forward to that.
Right. So the question is, how do you measure the speed of sound in just something like air? And this is something you can actually kind of do at home. If you just have a plastic tube like this, you can get a sound in here by just... You can whack yourself on, which I don't recommend. This one happens to be sort of soft. And when I do that, you can see this little frequency analyzer that I happen to have here tells us that this thing vibrates at about a frequency of 260 hertz.
Okay.
Okay? Or in other words, the air in here vibrates at 260 hertz. And then we have to understand that this thing is half a wavelength long. And to convince you that that's true, I brought my guitar in. And the way that a guitar string, the way a guitar string vibrates is that it's fixed at either end. When I pluck it, it has a big vibration in the middle. It's fixed at either end, and this is exactly half a wavelength of this wave. You can sort of imagine the wave going up and back down again. And it's the same thing is true for this piece of plastic. We have the air inside isn't moving in the middle at all. It's at rest, and in the ends it's vibrating, so that's half a wavelength. So if we just measure the length of this thing, it's a little over half a meter. It's 0.62 meters. Okay. If we double that, that means we get the actual wavelength, which is about 1.2 meters. If you multiply the wavelength, 1.2, by the frequency, 263, you get the speed, the velocity of the wave, which is about 330 meters per second. And that is the speed of sound in air. We can do the same thing in aluminum, and this is the most annoying demo ever.
It's a great demo.
It's a great demo. This is just a plain old aluminum rod, and we can get a wave traveling inside this thing, a standing wave too, just by getting some rosin on my fingers.
There it is.
This thing's spiking now.
Now where is it spiking? 4,180 hertz or something like that. And this thing, if we just measure the length of this puppy, it's about the same length as the other one. So this is half a wavelength. The wavelength is a bit over a meter, maybe 1.2 meters. We multiply that by 4,100 hertz, and we get the speed of sound in aluminum, which is about 5,000 meters per second.
Which is way faster than air.
Which is way faster than air. It's about 15 times faster. And when we measure the speed of sound in water, which we'll hopefully do next week, we'll find that it's about 4 times faster than the speed of sound in air. It's about maybe 1,500 meters per second. And that's kind of interesting. You know that sound travels in water, but maybe you don't have the experience.
Well, it would seem to me that it would go slower in water.
The way it works, it goes faster in solid and in liquids because the atoms and molecules are kind of packed together, and so when one jiggles, it jiggles the next one right away.
Oh, okay.
Since they're so close. And so the things really propagate very efficiently, and in water, sound propagates quite well. If you've ever been in a pool, and sometimes they have underwater speakers in swimming pools, you can hear those things pretty well. And also the way depth charges work in submarine warfare and stuff is you just have to set off an explosion. You don't have to be particularly close to the sub. That shockwave travels through the water really, really well and shakes up the boat and hopefully breaks it. So water's very good at transmitting sound, and we're going to use that next week when Dr. Z brings in this very cool ultrasound machine.
Okay, can you make the rod sing again?
I can do that.
Singing rod. Can you do this with just any piece of aluminum, and then you can determine a wavelength, or is it specially grade stuff?
No, this is a hunk of aluminum. If you get a nice piece of aluminum like this one's a little rough on the surface. That makes it easier to rub it. But yeah, anything will get a sound going in it. Okay. So this thing's pretty cool.
Matt Sellen, the wise guy, explaining the speed of sound for us on The Morning Show. We'll be right back.